So, we'll start a new lecture here and just discuss the contents of the last lecture briefly. So, in the last lecture we started our discussion on diamagnetic materials with a emphasis on sort of qualitative treatment of diamagnetic susceptibility, and what we found there was that the moment or the magnetization which is created as a result of application of magnetic field opposes the applied field. So, as a result the susceptibility is negative, and this diamagnetic behavior is inherent to all the materials because all the materials have electrons, and as a result no matter what is the eventually the type of material, diamagnetic character is always present. It is just that some materials have only diamagnetic behavior, that is why they are called as diamagnetic materials, but other materials happen to have other contributions such as paramagnetism, ferromagnetism, etc. Dominating over the diamagnetic character. So, as a result diamagnetic behavior is shielded, and since the diamagnetic susceptibilities are very small in nature, in number, they do not really show up. So, the next contribution that we talked about was paramagnetism, and this paramagnetism happens in materials where atoms have permanent dipole moments, but those dipole moments are randomly arranged with respect to each other because of thermal energy, and this thermal energy allows these dipoles to be at random orientation with respect to each other. As a result, the net magnetic moment of material is equal to 0. Now, when you apply field to such a material, of course, there is alignment of magnetic dipoles in the direction of applied field, and that results in a positive magnetization and positive susceptibility. Now, and what we found here was also that paramagnetic susceptibility was a temperature dependent entity, and this has a temperature dependent of the sort, so that it is called as Curie wise behavior, and the behavior is something like this. So, your 1 by chi starts from increasing as a function of temperature, or chi decreases as a function of increasing temperature. So, this is how you depict the behavior of a paramagnetic material. Now, lastly we looked at, because there is a quantum mechanical explanation, because the quantum mechanics says that everything has to be quantized. So, moment also has to be quantized, and as a result, and since you know that moment has contributions from orbit and spin contributions, in paramagnetic materials of interest such as transition metal elements, the magnetic moment per atom is spin dominated, whereas in case of rare earth elements, since the orbitals are far off, they do not get quenched. As a result, orbital magnetic moment also starts contributing. So, the this factor, which is g root j and j plus 1, it takes contributions both from spin as well as orbital, whereas from the spin contribution, spin contribution contributes mostly in the case of transition elements or d group elements, and the measured and experimental values, they match pretty well to suggest that that is indeed the case. So, I also suggested a couple of books which would be relevant for reading about magnetism. So, Solid State Physics by Charles Kittel and Solid State Physics by A.J. Decker. These are the two good books which you can go through for improving the understanding on magnetism, or as a supplementary reading in addition to this module. So, what we will do now is we will take up the case of another important class of magnetism. This is called as ferromagnetism. And this ferromagnetism is a very interesting phenomena. It has been observed since long times, since the times when iron is available, iron oxides are available, and these happen to, and the pieces of iron have always had this magnetic property. They have attracted each other, but the fundamental reasons of this behavior were not known, and it was merely an observation rather than a deep study of science into it. So, basically this phenomena happens in materials where atoms do contain permanent magnetic moments, but that is also true about paramagnetic materials. So, what is the difference here? The difference is, while in paramagnetic materials the dipoles are magnetic dipoles, or atomic spins are randomly distributed with respect to each other, the magnetic moments of atoms are randomly distributed with respect to each other. Here you have a alignment which gives rise to a non-zero magnetic moment even in the absence of applied field. So, the picture is something like this. So, you have these, for instance, atoms, and these atoms have magnetic moment, which gives you a random sort of moment, but it's not random enough to give you 0 moment, something like that. So, it's a highly idealized picture. So, this gives you, this is in the situation when H is equal to 0, but M is not equal to 0. So, there is a finite magnetic moment in the absence of applied field. Now, when you apply field to such a material, so when, let us say, I depict by different color. So, if I apply field H to such a material, then all the magnetic moments eventually align themselves in the direction of applied field. I think two moments have been drawn here. So, should be corrected. So, the picture now is, so when H is not equal to 0 or H is greater than 0, then M is very large as well, because all the moments align themselves in the direction of applied field. So, this state, this color says alignment of atomic magnetic dipole. This dipole term is only an analogous term to the charge dipole, but dipole essentially means that you have dipole, you have two different poles. So, it is just that because you have magnetization, magnetic moment vector pointing from this direction that direction. So, you have one pole or you have another pole, and in magnets it is seen as north south as well. So, that is why it is called as magnetic dipole as well. So, by analogy it is called as dipole. So, let us stick to this term magnetic dipole. So, alignment of atomic magnetic dipoles in one direction, in the direction of applied field when the field is large. So, now these materials typically they contain regions of, again just like ferroelectric materials, they contain these regions of ordered magnetization. So, or you can say ordered regions of single magnetization, which are also again called as domains, and these domains happen to be arranged in such a manner, so that when there is no field, there is a remnant magnetization. So, that we will look at the reasons for why domains exist and how do they grow and change their orientation with respect to applied field a little later. But just like ferroelectric material, also when you change the temperature for this material, then this material also undergoes a Curie transition. So, ferromagnetic materials also undergo a transition from ferromagnetic state to a paramagnetic state, or you can say a non-magnetic state, because paramagnetic is non-magnetic in the absence of applied field at a temperature T is equal to Tc, and this is called as Curie temperature. So, however, the difference is, while in ferromagnetism we talk about first order, second order transition, here we do not talk about that kind of transition, simply because in ferroelectricity the transition is associated with a phase transition. There is a change when you heat the material from a low symmetry to a high symmetry phase, whereas this is not a strict condition, or this is not necessarily a condition for ferromagnetism. So, this is not a necessary condition, phase transition is not a necessary condition for ferromagnetism. That is why you do not associate it with the phase transition as such. So, you just talk about a Curie temperature, which is a transition temperature from ordered ferromagnetic state to a disordered paramagnetic state. So, what happens in a ferromagnetic material also like a ferroelectric material, when you so what we are going to draw is basically switching under a varying magnetic field. So, what you have here is essentially material in the virgin state. Virgin state means as prepared state does not have any magnetization, and then this magnetization increases, and then it saturates as the field increases large values, and then it comes down and it follows this kind of hysteresis. It is not looking very nice here, but the point is here these two values m r and minus m r, they are exactly equal and opposite to each other. And similarly, you have two field values at which the magnetization is 0, they are called as plus h c and minus h c, and this curve is called as a MH curve or magnetic hysteresis curve. So, what you have a hysteresis when you switch a ferromagnetic material under the varying magnetic field. So, you start from 0 magnetization in the virgin state, and that is because the domains are randomly oriented with respect to each other, giving rise to 0 net magnetization. When you increase the field, eventually a point comes where all the domains are aligned in the direction of applied field and you get a saturation magnetization. And once you have all the saturation, once you have alignment of all the magnetic dipoles along the direction of applied field, you have nothing else to be aligned, and so further increase in the field does not result in any increase in the magnetization. And when you decrease this magnetic field, at 0 magnetic field there is a remnant magnetization, which means there are domains. So, there is a net alignment of domains along the direction of applied field, or there is a net alignment of domains in one direction, and those domains happen to be larger in number or larger in volume as compared to those which are oppositely oriented. So, the net magnetization is finite, and when you if you want to bring back material to this state, you need to apply an additional field in the opposite direction, so that you have volume of domains of one orientation equal to volume of domains of another orientation, giving rise to 0 magnetic field, 0 magnetization. And then when you want to achieve this state again in the opposite direction, you need to increase the field further, so that the domains of opposite orientation are larger in number or monodomain state occurs. And when you again bring the field back to 0, then again you have similar state as you had at plus mr, as minus mr, and this cycle continues, and this is called as a magnetic hysteresis curve, or ferromagnetic hysteresis curve to be precise. And this Hc is called as again coercive field, Hc and minus Hc, and this Mr and minus Mr are called as remnant, REMANENT. And the energy which is dissipated now, because you have hysteresis, which means you have some energy dissipated, and this energy basically defines the nature of a energy dissipation defines the nature of a ferromagnet. Unlike this term is not used in used for ferroelectrics in general, but for ferromagnetic materials you have this term which defines whether you have a soft magnet or whether you have a hard magnet, and we look at it in a while. So, what happens here is and of course, we are talking here in terms of domains as well. We have not introduced how the domains in these materials form and how do they switch. So, we will look at that in a little while as well. This is what is a characteristic of a ferromagnetic material. Now, examples of ferromagnetic materials are mostly D elements like iron, nickel, cobalt, all of these are ferromagnetic in nature. And then the paramagnetic materials are different actually. Paramagnetic materials are the early transition metals like titanium and calcium, etc., which are in the top row. And then you have some oxides as well, which are ferromagnetic in nature. So, oxides such as chromium oxide CrO2, SrRuO3, and some doped oxides as well. So, A is the dopant, and doped manganites basically. these happen to be ferromagnetic in nature. So, there is a host of materials which happen to ferromagnetic in nature, but most important of them which have been studied a lot are these metallic elements which have of course a permanent magnetic moment, and that is why we chose them as an example, but they do have a strong ferromagnetic character. Now comes a point, first of all, what these we have introduced the term domain. So, the question which comes now is how do these domains form in the ferromagnetic material, and how do these domains move in the ferromagnetic material. So, there are essentially variety of reasons. We will look at these domains first in the context of switching, and then we will introduce the physical explanation of what is the reason of forming domains in the ferromagnetic material. So, we will first look at the hysteresis behavior in terms of domain movement and in terms of the energy which is dissipated. So, or rather behavior of ferromagnetic hysteresis. Now, so we have said that you have ferromagnetic material like this, and you have so this is how it looks like. So, you have plus Mr and this is your M minus Mr plus Hc and minus Hc, and this should be a straight line actually. Okay. And this is called as saturation magnetization. So, plus Ms and this is called as minus Ms. So, these are equal and opposite states, and this is again has advantages in the form of their applications. So, you start at this point A, or let us say O, and initially what this point corresponds to a virgin state, and what this means is that M is equal to M net is equal to 0, there is no magnetization, and then you slowly start increasing, and then it goes like this. So, you have these different regions of domain growth. Here you achieve complete alignment of domains like this, and here it may be at this point it could be. So, field is like this, domains could be like that, and at this point you would have, let us say, different regions. So, you would have situations like this. So, you do not have net, you have very small net magnetic moment, and so on and so forth. This keeps going on. So, now depending upon the parameters of this hysteresis loop, the behavior of magnetic material is defined. So, for typically it is defined in terms of ease of magnetization, and this ease of magnetization essentially is about the coercive field. Typically, a large coercive field would mean that domains are not easy to switch, which means you cannot reorient the domains without applying a large field, and that is why these large coercive field materials, so materials with large Hc, they are called as hard magnets. They have typically large magnetization, but they also have large Hc. What it means is that essentially, because when you are going from this state, so the domain structure at this point would be something like this. So, let us say it is a very simplified picture. So, this would be, let us say, this, and then let us say this, and something like that. So, you have a net volume of domains which are favorably oriented. Let us say this is the direction in which the original magnetization was done. So, this would be the total volume, which is, so this volume plus this volume minus this volume plus this volume gives you a finite magnetization. Now, when you want to go to this state, which means you have 4 equal quadrants. So, let us say you have a picture like this, and this means that net magnetization is equal to 0. Now, how would this occur? This would occur by some sort of movement of domain wall. Now, how the domain walls move, that I will come to a little later. It has to happen by shrinking of these domains which are favorably oriented, or nucleation of, or some other mechanism. I'll not bring to, let's not talk about the term nucleation, but it has to happen by some movement of this domain wall, which is the boundary between these two domains, and that basically determines, and that basically requires a particular force. And this, some domain walls may require larger force, some domain walls may require smaller force. So, the domain walls which require larger force for their movement are typically materials with higher coercive field, and domain walls which move easily at a small fields, they are called as, we will introduce another magnet which is called as soft magnet. So, materials with soft magnets, and typically this would characterize harder domain wall movement, and this would be easier domain reversal. Domain wall movement or reversal is the same thing. Okay. So, this is a typical difference between these two different kind of materials. So, if I want to draw the magnetic hysteresis curve of two different kind of materials, then if I draw it on the same plot. So, if this is my material with, let me just draw two different lines. So, this is one kind of magnet, and if I draw another one which is something like this, let us say, just for the sake of illustration, I am going to just make it slightly different. Then do not look at the magnitude of MR, that is just for sake of illustration, but what is important here is this HC and this HC minus HC, they are smaller than the green one. So, this would be called as BH or MH curve for a soft magnet, and this would be called as a BH or MH curve for a hard magnet. All right. So, this is the typical differentiation. The power which is dissipated, no matter what the type of magnet it is, you still have dissipation of energy in the form of hysteresis. So, this power which is dissipated is nothing but A MH, area of this MH curve, multiplied by the volume of material and multiplied by the frequency in hertz. So, this gives you what is the power which is dissipated inside a ferromagnetic material, and typically and naturally the larger the power dissipated, you would tend to think that the material is a hard magnet. So, soft ferromagnets have a smaller power dissipation as compared to hard ferromagnet. So, in general, hard ferromagnets have larger power dissipation, and these soft magnets, as a result, the soft magnets with small Hc and reasonably large Mr tend to be used in cases where the losses must be smaller, power dissipation must be smaller. As a result, they find applications in transformer cores and motor cores where the energy dissipation due to AC fields is low, and hard magnets on the other hand find application in those areas where you want the magnetization to be reversed with difficulty, where the domain reversal has to be difficult. So, they find applications in permanent magnets, memories, because you do not want your data to be lost. So, you want to retain that particular state, which is, so I didn't introduce this, but just like a ferromagnetic material, these states which are plus MR and minus MR can also be used as 0 and 1 state of memory in a binary memory data storage. So, if you have that kind of memory device, then you do not want your data to be erased, which means you want that 0 or 1 state of the memory to be preserved when you do not want to, when you are not doing anything purposefully. So, as a result, hard magnets are used in applications where you do not want domain to be reversed easily by small fields, and soft magnets of course in applications where energy dissipation is an issue. So, this is the kind of picture which emerges of ferromagnetic material. Now, what we will look at ferromagnetic material in a little bit more fundamental detail. So, the first thing in that line is the formation of domain in these materials. Now, domains, again, as we know in from our discussion in ferroelectrics, that they are regions of uniform magnetization. So, you can have a state like this. So, let us say this is north, this is south. So, this would be, so if this whole volume of this material has magnetic dipole pointing in this direction, then this is a monodomain state. So, this is a domain. Okay. So, but just like in, again refer back to ferroelectric material, although the reasons here are different than ferroelectric material, but again it is energetics. So, now when you have this monodomain state, now this monodomain state, the Hund's rule allows the spins to be aligned in one direction, and then because of certain reasons all these atomic spins are also aligned in one direction. They of course obey Pauli's exclusion rule, but there is a term called exchange energy, and this exchange energy is essentially, without violating the Pauli's exclusion rule, it allows all these spins in one direction, that is called as a spin up direction. And this is, and for certain ferromagnetic materials, the exchange energy, which is nothing but product of different kind of spins. So, this exchange integral is proportional to sum of spin moments of all the atoms, and this exchange energy happens to be minimum for ferromagnetic material when the spins, all the spins are aligned in one direction, and that is what makes one domain. So, this domain essentially is as a result of this small exchange, or let us say minimum exchange energy. Now, so you can have throughout the volume of the material all the domains aligned in all the spins aligned in one direction. That is fine, but what is the problem with this? Because when you have such a situation, then you have very large surface magnetization energy, and this is called as magnetostatic energy. So, you have very large flux lines on the surface of the material. So, as a result you have very large surface magnetic energy or magnetostatic energy, which makes this structure unstable. So, what happens rather is you have this state in which you have single magnetization, and this has consequences in terms of large surface flux. Now, this tends to break this single domain state into a rather more stable state. So, let us say if I have two regions of the material now, with one region spin up, one region spin down. Now what I have is, I have this north, this south and this north. So now I can have the flux lines only on this side. So the surface flux density has gone down, which means the magnetostatic energy of the material has gone down. I can make this slightly more different if I have a situation like this. So let us say this is spin down, this is spin up, and this again would be spin up, and you can have different regions here. Again you can have, let us say, you need to always have this consonance in terms of, let me just make some changes here. Let us say situation is something like this. Okay. So this is spin down. So what you are going to have here is spin left, spin right, and this would be spin right, spin left. And this again you have north south combination, and this gives you much smaller. So as you go from this configuration to this configuration, reduction in surface flux density. But what you also have here is, although you have reduction in the surface flux density or decrease in the magnetostatic energy, but what you have also, you have introduction of these what you call as these regions, which are nothing but domain walls. And domain wall, as we have seen before, is a surface. So what you have here is, on one hand you have reduction in the surface flux density, on another hand you have increase in the domain wall area, and this requires a positive energy, surface energy. So as a result, gamma requirement, gamma is the typical term for surface energy, that gamma increases. So one needs, so the stable domain configuration is something where the net free energy term, which includes these two terms, adopts a minima, and that would be the stable domain size, and the analysis would be based on a similar line as against the analysis that we did for ferroelectric material. Basically you have to differentiate that free energy term with respect to the domain size and find out a stable domain size for a given combination of surface energy and the surface flux density. So there are variety of material there are variety of energies which affect, I have given you very simple representation of this energy balance, but there are variety of energies which affect this kind of scenario, and these energies which basically domain size is dependent on variety of these energies, and basically the balance between these energies is because some of these energies are positive, some of these energies are negative. So of course you have exchange energy, and you have basically magnetostatic energy, which is because of the surface, which is essentially due to surface flux density. And then you can also have magnetocrystalline energy, and this forces this basically energy is due to the coupling of magnetic moments with respect to the crystal lattice. So the direction of magnetic moment is coupled to the lattice. So any change in the lattice structure or parameter forces the change in the magnetization. So as a result, hard and easy access may arise. And then you have magnetoelastic energy, and which is due to changes in the lattice parameter as a result of spin orbit coupling. So both of these are essentially coupling of structural parameters with respect to magnetization. For a given material they are constant, for a given material exchange energy is also fixed. So what is actually varying is this energy and finally you have domain wall energy. So, combination of these two energies essentially governs the size of the domain in a similar fashion as it happened in the ferro electric materials. So, essentially multi-domain state requires many interfaces, but this configuration is essentially thermodynamically stable simply because it leads to overall reduction in the free energy of the system. So, essentially so once you have a stable domain configuration, what you have is a multi-domain state, and this multi-domain state, as we have discussed, is dependent upon the combination of various energies, most importantly the magnetostatic energy and the domain wall energy. So, these two decide the size of the domain in a given material, because the other energies are nothing but function of the material itself, and they fairly remain constant. And the nature of this, now the question, another next question is, in case of ferroelectric material, when you went from one domain to another domain, there was a change in the polar vector, but this domain wall was a very narrow domain wall. There was not the domain wall was wide of the width of the domain wall of the order of a lattice parameter, or maybe 2 lattice parameters, 3 lattice parameters. In case of magnetic materials, the domain wall has a slightly different nature, and that is why in these materials, these are called as often Bloch walls, after the F. Bloch, who in 1932 proved that magnetization cannot change discontinuously at the domain boundary. So, unlike in ferroelectric materials, if you remember, in ferroelectric materials, if you had region of polarization like this, then this was the domain boundary, and you had next region of polarization like this. At the domain wall, the ferroelectric polarization P changed abruptly. So, the domain wall width was insignificant, it was very small, of the order of lattice parameter or 2, whereas in case of ferromagnetic material, it was proven by energy calculations that this magnetization M in one region cannot abruptly change at the boundary into another region. So, this boundary happens to be a region which is fairly big. So, this boundary, when you look at it microscopically, it is something like that. So, you go from one to another magnetization, it slowly goes like this. So, this is how it varies in nature, and this is just this domain wall width, and this domain wall width happen to be of the order of 10 to 100 nanometer, and which is much bigger than the domain wall size in ferroelectric materials. In ferroelectric materials, we are talking of domain wall size of the order of couple of lattice parameters, and which is a typical lattice parameter would be somewhere like 4 to 5 angstrom. So, this would be somewhere like 10 to 15 angstrom in size in ferroelectric material, whereas in ferromagnetic material, if you look at the difference, so this is like 1 nanometer, and here talking about an order of 2 magnitude higher wide domain walls. So, there is a gradual change of magnetization at the domain boundary, unlike in the ferroelectric material, and this actually results from the change in the way these domains, the domain reversal takes place. In case of ferroelectric material, we looked that the new domains nucleate, which are in the direction of applied field, and they grow at the expense of these older unfavorably oriented domains. Here what happens is that you have growth of previously slightly favorable, the most favorably oriented domains at the expense of the old domains. So, there is no nucleation phenomena, it is only the growth of old domains which further realign themselves in the direction of applied field. And as far as the energy of this boundary is concerned, these boundaries can have energy anywhere around 10 to the power minus 4 joules per meter square. This is the domain wall energy in case of ferromagnetic materials. So, this is after F. Bloch, who prescribed this theory in 1932, that the magnetization in a ferromagnetic material cannot change abruptly at the domain wall. It has to be a gradual process, and this was based on the theoretical calculations he made on these on the ferromagnetic systems. So, in the ferromagnetic material, the way domains grow is, so you have a situation. So, let's grow. So, this is the ferromagnetic loop, all right, and okay. So, this is the virgin state of the material. So, let us say the domain structure at this point is something like this. If I draw a different color, and at this point what you had was a domain structure like this. So, let us say this is in this direction, this is in this direction, and this is in this direction, this is in this direction. So, the net m was equal to 0. Now, what happens in these materials is that when you start applying the field, so let us say the field initially the field is always in this direction. So, let us say the field is in, so this is when h is equal to 0. Let us take somewhere around this point. So, the field is in this direction, and if we just look at this picture, what happens is the most favorite, or just for the sake of illustration, I will make the field slightly in different direction. Okay. So, let us say the field is in this direction. Okay. So, what happens here is, if the field was in this direction, then the most favorably oriented domain was this domain and this domain. Okay. So, what happens is these domains grow at the expense of these other domains. So, what you have here is, you have the growth of these domains at the expense of. So, this domain for instance gets bigger, and let me just, and this domain gets smaller. So, as a result you have m which is not equal to 0. Now, let us say when you reach somewhere here, so you do not have any nucleation of new domains, rather what you have is growth of the old domains itself, the most favorably oriented old domains. So, when you reach to this point for instance, then you have, let us say, so your field was in this direction. Oops. So, I'll do that here maybe. So, this is your domain structure. So, if your field was in this direction, but the domains were aligned in this direction. Now, since the field was in this direction, these domains also now have to rotate in this direction. So, when you come to this point, then field was in this direction and the domains were also in this direction. So, this is how the domains move in these materials, and when you come to this point, then these favorably oriented domains, they remain, some of these other so they tend to flip back, because now the field intensity is changing. So, as a result now you have some domains of other kind which are forming. So, you have other domains which are forming. So, as a result you have m not equal to 0. So, m is equal to mr, and here you had m is equal to not equal to 0, and this was the situation where m was equal to ms. So, from ms to mr there is a slight drop because of formation of oppositely oriented domains, and this happens by gradual flipping of some of the magnetic dipoles in this otherwise monodomain region, and the whole system continues until you reach, whole process continues and the formation of, now when you change the field back to this direction, the field direction has happened in this direction. So, the domains of, so there are some domains in this direction, some domains in this direction. So, this gives rise to m is equal to 0 at h is equal to minus hc, and this whole process continues in the similar fashion. So, here the difference with respect to ferroelectric material is domains which are favorably oriented grow at the expense of unfavorably oriented domains. So, it is only a growth phenomena, rather it is not a process of nucleation. So, there is no nucleation in growth phenomena like in ferroelectric material. So, that is a crucial difference with ferroelectric materials here in terms of domain growth in ferromagnetic materials. Now, what we are now going to look at is essentially the microscopic region for magnetization in ferromagnetic material, and for this we will look at what is called as molecular field theory. And this comes from the fact we are saying that each of these atoms have permanent magnetic moment. So, nickel has a permanent magnetic moment, iron is permanent magnetic moment, but what is that which leads to this ordering of spins? Because what we are saying is that all these spins are aligned in one direction, giving rise to a domain. So, what does lead to the formation of this single domain state, and what is the effect of ordering on the magnetic moment of this material? And this ordering is, in the very crude language, you can call this a neighborhood effect, which essentially gives rise to an internal field as postulated by Wies earlier in 1907. So, who postulated that this alignment of magnetic moments in this uniform region is because of neighborhood effect or because of presence of some internal field. And this field was also called as, at that time, molecular field. And this molecular field, just like as we saw in ferromagnetic materials, just before the Clausius-Moretti relationship, you had internal field. So, on the same lines, a molecular field was conceived, and this field was thought to promote this alignment of spins in one direction, giving rise to a ferromagnetic interaction. And so, this molecular field or internal field is called as Wies molecular field, and this is denoted as HW. And so, let us say this HW. So, the internal field inside the material now will be the applied field plus this molecular field HW. So, you have the field which is applied. Typically, if you take this internal field equal to 0, the total field which the material experiences internally will be only applied field. But if you have some internal extra field present, because which leads to alignment which was called as molecular field, then the whole internal field gets modified as H plus HW, and this HW was defined as some constant gamma multiplied by magnetization, and this gamma is called as molecular field constant, and this gamma multiplied by magnetization is the extra effect which is present in the ferromagnetic material. So, when you replace this H, so you know that m by H is C by T. So, this H is the internal field in this case. So, you replace this m divided by H plus gamma m. So, let us say this is Hi, and this Hi is equal to applied field in paramagnetic materials is equal to C by T, and if you rearrange this, what you will get is m is equal to Ch divided by T minus gamma C, or m divided by H is equal to C divided by T minus theta. So, this is theta, and this has a of course a unit of temperature, because this is nothing but C divided by T minus some Tc or theta, and this is called as the Curie temperature, and this whole thing is called as Curie-Weiss law. So, the Curie law, which was followed by paramagnetic material, has been modified into Curie-Weiss law with the introduction of this molecular constant, which is the Weiss constant, also into this susceptibility expression. So, as a result, when you plot this magnetization versus temperature for a ferromagnetic material, this shows the following trend. So, you have magnetization starting at Ms, and this magnetization drops to, so you would expect a transition temperature, and this, because of Curie-Weiss behavior, it dies off slowly near Tc. So, this is the ferromagnetic state and this is the paramagnetic state, and in contrast, if you plot the susceptibility, so this is temperature, and if you plot 1 over chi, 1 over chi has a behavior which is something like and this is called as theta. So, this is your paramagnetic state and this is your ferromagnetic state. So, this is the behavior of, so Ms, it starts off almost flat, and then it drops near the Tc, and then near the Tc it dies off slowly, leading to zero magnetization, whereas 1 over chi, it's a signature of basically a phase transition to a spontaneously ordered phase, ordered in the sense of ferromagnetic ordering. And so essentially you might have this susceptibility, it drops off fairly rapidly up to theta as the temperature is decreased, and then it slowly dies off near the theta. So, this is how you depict the ferromagnetic to paramagnetic transition, and this would correspond to a Tc. So, again it follows a similar Curie-Weiss behavior with the introduction of this molecular constant, but the real picture was slightly different. The real picture was there is no as such internal field, but rather what you have is what is called as exchange energy, and this exchange energy is a very funny quantum mechanical concept, and what basically it's a exchange integral essentially J, which is proportional to product of Si S j, which is the spin magnetic moment of all the atoms, and you sum them together, and this J happens to, in a ferromagnetic material, this J happens to adopt a minimum for a parallel configuration, but for anti-ferromagnetic materials, as we will say later, this J happens to adopt in the anti-parallel configuration. So, this J integral, which is which represents the exchange energy, which plays an important role in the alignment of these spins in one direction. It's not something which is, I mean, you can still call it a internal field, but it's not internal field as such. It's this exchange energy which is because of alignment of spins, which is because of product of these spin magnetic moments, and this is essentially because of coupling of the balance between various energies in the system, which gives rise to this kind of effect. So, another difference of exchange energy with respect to this so called molecular field is that whereas molecular field is a large area concept, the exchange energy is a short range concept. So, this is one of the differences that was later produced, later explained by quantum physicists. And another thing is this this magnitude of internal field, if you work out just by taking the magnetization which is shown, for instance, this exchange energy which is based on this internal field. It is given as mu b HW. If you just relate it to thermal energy kT at Tc, so this HW will work out approximately kTc at divided by mu b, because at thermal at Tc this exchange energy or the internal energy will be overcome by thermal energy. So, that is where they become equal, and if you work out this HW, this is very high, this is 1 kilotesla or so, and these kind of magnetic fields cannot even be produced on best of the machines in the world. So, this concept of internal field is slightly wrong in that sense. Rather, exchange energy, which later was explained by quantum physicists, which is based on the spin alignments and minimization of energy, is a far more accepted phenomena, but we will not go into discussion of that because it is beyond the scope of this course. But if you are interested, you can read on variety of books on ferromagnetism. I will give you some titles in the next class where you can read about it. And so, essentially you have a ferromagnetic. In this class what we have discussed is, we have another class of materials which are called as ferromagnetic materials. The difference between these and paramagnetic materials is they have large positive susceptibility, which means large magnetization, and it happens in materials with permanent magnetic moments, but these moments are aligned with respect to each other thanks to the exchange energy minimization. And this exchange energy is a quantum mechanical concept again. So, we'll not take this into discussion in this course, but essentially it gets minimized in ferromagnetic materials when you have parallel configuration in one direction. And these materials also show similar hysteresis loop, just like in ferroelectric materials when they are switched. So, you have a MH curve. Width of this curve governs whether you have a soft magnet and hard magnet, and again you have this concept of domains, and domains are nothing but regions of uniform magnetization, and these domains form as a result of balance between various kind of energies, most importantly the domain wall energy and the magnetostatic energy, and this governs the minimum size of the domain that you must have. And the materials also follow what is called as a Curie wise behavior, which means you have a drop of magnetization to paramagnetic state at a temperature which is called as a Tc or transition temperature. So, we will finish this lecture here with this summary. In the next class, we will take up the remaining causes of magnetism with a more strong focus on magnetic ceramics, which is ferrites, which fall in the category of ferrimagnetism, and this is under broader umbrella of antiferromagnetism. Thank you.